discuss about a question paper from Air Safety Officer's post from Aeronautical Engineering stream. So today we will be going to see about propulsion questions. So in this paper, like I can see around 8 questions being asked from core propulsion. So let us see like all the questions what is being asked. So the first question is coming out of a rocket propulsion part. So they're asking what is the thrust equation for a rocket engine. They're also giving the notations they are going to use, where M is mass flow rate of a propellant, PE is the nozzle exit pressure, PA is ambient pressure, AE is area at the nozzle exit. So if we look at the rocket motor or rocket engine, so we usually have a combustion chamber where the combustion of a fuel and oxidizers takes place, and it will expand through a converging nozzle, converging diverging nozzle to give a momentum thrust. Okay, so the combustion chamber properties are P naught and T naught, and the nozzle exit area will be AE, the nozzle exit plane pressure will be PE, and the ambient pressure can be PA. And velocity at which the propellant is expelling out of the nozzle, let us call it as VE, and the mass flow rate of the propellant, call it as M, as denoted in the problem. So we know that the thrust produced by the rocket engine, so like if you do the control volume analysis for this one, the moving control volume analysis, we would get a thrust equation something like a momentum thrust plus the pressure thrust. So the pressure thrust will be the differential pressure in the exit plane of the nozzle, right? So it's a very straightforward question. So the total thrust is a combination of momentum plus pressure. So by looking at the given options, the only option A is correct, and option C and option D we can straight away omit because they are dimensionally not even close to thrust form. So option B and option A, if you see, this will add up the pressure, so it is not the pressure thrust part we will expect. So only option A can be correct in this case. Okay, so then moving on to the next question. Again, it is coming out of a rocket propulsion. They're asking a rocket engine with a chamber pressure of 4.5, it's not 4.5 megapascal, and nozzle throat diameter of 110 millimeter, produces thrust of 17 kilonewton by consuming propellant flow rate of 7.5 kgs per second with calorific value of 25 megajoules per kg. If the flight velocity happens to be 850 meters per second, what is the effective exhaust velocity? So again, we can refer back to the same schematic what we have drawn for the last problem. They have a rocket that is propelling in the atmosphere. Which has a chamber pressure, let us denote it by P naught. of 4.5 megapascal, and we are adding the heat into the combustion chamber with a calorific value of the fluid is 25 megajoules per kg, and they're given the flight velocity, not the exit plane velocity. So the flight velocity is 850 meters per second, and this is producing the thrust of 17 kilonewton with the mass flow rate of the propellant given by 7.5 kgs per second. And they're also given the throat area of the nozzle in terms of the diameter of the throat, then 10 millimeters. And they're asking us to calculate the effective exhaust velocity. So see here in this problem, the total thrust is given. They are not given whether it is a momentum thrust or there will be a pressure thrust component involved in that or not. But the total thrust produced by the rocket engine is combination of momentum thrust plus the pressure thrust that we just saw in the last problem also. And how do we define the effective exhaust velocity? The exhaust velocity is something at which the fluid is exiting from the nozzle exit plane. The effective exhaust velocity would be what if all of this thrust combining momentum and pressure is produced through a momentum thrust. So then if I can express this thrust to be equal to a mass flow rate of the propellant times the effective exhaust velocity. So in a way that the effective exhaust velocity would look like, if you combine these two equations, that is VE plus PE minus PA times AE over m dot, right? So as the problem statement is already stating what is the total thrust produced by the engine, and they are also given what is the mass flow rate involved in the problem. So we can directly calculate a effective exhaust velocity as a thrust over mass flow rate of the propellant. So thrust is 17 kilonewton. The mass flow rate is 7.5 kgs per second. So if we use the given data, we should be able to get the effective exhaust velocity something around 2266.7 meters per second. It's a straightforward problem. So in this problem, like there are so much of data which are redundant. So only the data which we are required. So that is thrust and mass flow rate. Other data is not useful in solving this problem. Okay. So the next problem we have here is this multiple choice question. The ratio of thrust power to the rate of kinetic energy available at the inlet of the exhaust nozzle is. Okay. This is again a straightforward problem. They are giving a definition of some sort of variable. So they are given, let us keep this as unknown quantity, the left hand side. So the definition they are given is a thrust power to the available kinetic energy at the inlet. So that will be half m dot Cj square minus Ci square, where Cj is the exit plane pressure, Ci is the inlet plane velocity. So this definition is precisely the definition of propulsive efficiency. So remember, propulsive efficiency is nothing but out of the available kinetic energy, how much you are converting it back to thrust power. So this definition is nothing but a propulsive efficiency. The thrust coefficient is different. So we define a thrust coefficient something like the thrust produced by the engine to the P naught and AT. P naught is the stagnation temperature in the chamber, AT is the throat area. And specific impulse, we define it as the impulse per weight flow rate. So that is nothing but, so we can show that for a constant thrust production, F over m dot P times G naught. So that is specific thrust, a specific impulse, and a thrust efficiency is something like they are simply keeping here. So we really don't use any definition like thrust efficiency in the literatures. So the only option here is a propulsive efficiency. That is correct. Okay. So then we have the next question, that is again a numerical type. So here you see a booster rocket engine with nozzle exit diameter of 225 millimeter is designed to propel a satellite to a altitude of 20 kilometer. Fine. The chamber pressure at 12 megapascal is expanded to exit pressure and temperatures of 105 kilopascal and 1400 Kelvin respectively. If the mass flow rate happens to be 15 kgs per second, what is the exit jet velocity at altitude of 20 kilometer? Okay. So they are given the molecular weight of the propellant is 25 kg per kilomole. Assume one dimensional flow at the exit of the nozzle and assume ideal gas flow. So again in this problem we are given many data actually. So let us try to model this problem. So we have a, say I have a rocket engine like this. So we have a stagnation pressure in the chamber is given to be 12 megapascal, and they are also given the exit area information of the nozzle, that is exit plane diameter is something around 225 mm and exit plane pressure is 105 kilopascal and exit plane temperature is something around 1400 Kelvin. Exit the mass flow rate of the propellant is 15 kgs per second, and they are asking us to calculate the exit plane velocity. So the other information is given as the molecular weight of the propellant is 25 kg per kilomole, and they are asking us to treat the flow in the nozzle is ideal, so that is isentropic flow. So from this one we need to first calculate the gas property, that is a gas constant. So that can be calculated as a universal gas constant divided by the molecular weight. So universal gas constant is 8314 8314 joules per kilomole per Kelvin divided by molecular weight 25 kg per kilomole. So kilomole cancels. So we will left with 332.56 joules per kg per Kelvin. Okay. So now looking at this problem, what we have to calculate here is the exit plane velocity. So the mass flow rate can be calculated using the exit plane information, that is a density at the exit plane, velocity at the exit plane, and area at the exit plane. And using the perfect gas law, P is equal to rho RT. So I can replace density as pressure and temperature information. So I can write it as PE by RTE times velocity times area is nothing but pi dE square over 4. So all the information except for velocity is known in this particular relation. So we can express this relation for exit plane velocity, that is VE is equal to 4 m dot R TE divided by PE times pi dE square, right? So if we substitute all the numbers, that is mass flow rate is 15 kgs per second, the gas constant is 332.56 joules per kg Kelvin, and temperature is 1400 Kelvin, divided by pressure is exit plane pressure, remember, that is 105 kilopascal. So pi into 225 into 10 to the power of minus 3 whole square. So we should be able to get an exit plane velocity of around 1672.8 meters per second. So if you look at the given options now, yeah, so that is close to 1673 meters per second. Fine. Then we have a question. This is very interesting question. Like they are given the statements and we have to choose the correct statements among the given statements. Consider the following statements regarding flow in the nozzle for exhaust velocity. The statement one is the flow in the nozzle is 3D in nature and temperature, pressure and composition of gas vary along the length of the nozzle. Then the statement 2 is the flow becomes more complex due to the presence of a shock wave and a flow separation in the nozzle. The statement 3 is the shape of the nozzle does not affect the thrust produced by the rocket engine. Okay. The first two statements are obvious. In a realistic nozzle, we do see a 3D nature of flow. Remember, whenever we do the quasi one-dimensional flow analysis, our assumption is like we are assuming flow to be one dimension. That is an assumption to make an analytical model. But in the realistic scenarios, we do see a flow to be as a three-dimensional nature and viscous. So because of that, the compositions and other things, because the temperature, enthalpy, everything is varying as the flow expands through a nozzle. So this is true statement. And the second statement, that is just a continuation of the first statement. The flow becomes more complex due to the presence of shock and flow separation in the nozzle. Of course, whenever we treat the realistic scenarios, we do see a boundary layer growth because of the viscous action, and if there is a shock wave that can be present if there is a pressure difference in the exit plane of the nozzle and the ambient conditions. So we can see the shock waves. So the moment when we see the shock waves, across the shock the pressure jumps, there will be an adverse pressure gradient that can actually separate the flow in the nozzle. So it becomes much more complex in the realistic analysis. So the statement 2 is also correct. If the statement 1 and 2 are correct, then the statement 3 cannot be right, because the shape of the nozzle does not affect the thrust produced by the rocket engine. That's what they're asking. But thrust is exactly dependent on the exit plane conditions, that is mass flow rate times velocity plus a pressure thrust. And since this velocity at the exit plane is highly dependent on the flow within the nozzle, because the flow has to expand to get to this velocity, so it is highly dependent on the shape of the nozzle, which dictates how the exit plane velocity should look like. So this statement cannot be right. So the statement 1 and 2 are correct. Okay. Then moving on to the next question, we have the question on ramjet. Consider the following statements for ramjet. It is a form of jet engine where incoming air is compressed by a rotary compressor. The statement 2 says it cannot produce thrust at zero airspeed. And the statement 3 says for supersonic ramjets, supersonic flow is decelerated to subsonic at inlet. Okay. So in this question, let us try to make a small schematic of a ramjet over here. So we have an incoming air that will be compressed through a supersonic diffuser. Then I will have a combustion chamber where energy being added. Then the flow will expand through a converging diverging nozzle to give a supersonic flow at the exit. The first statement says the incoming air is compressed by a rotary compressor. By definition, ramjet uses an idea of ram pressure rise without any moving parts. Pure geometry and gas dynamics will play a role here to compress the gas or the air which is coming into the engine. So this statement is not correct. There will be no moving parts, and it cannot produce thrust at zero airspeed. That is true. Why? Because the ramjets, to start the ramjet, we have to get to an altitude or the and the speed that is at which is operating by some other means, either carrying them in the supersonic aircrafts or launching it through some launch pads. So we have to uh, provide that condition at which it can start. So it has no static thrust. So this statement is true. And of course, the statement 3 is also correct, because in the ramjet, the combustion happens at a subsonic speeds. So in the intake, we have to reduce the incoming supersonic flow to a subsonic flow when it enters the combustion chamber. So only the scramjet that operates with a supersonic combustion, since they are asking about supersonic ramjets, so the flow is reduced to subsonic speeds in the intake. So the statement 3 is also correct. So in this question, options 2 and 3 are correct. 1 is not correct. Okay. So then we have a question on turbo rocket. Consider the following statements regarding turbo rocket engine. So their saying it is a type of non-air breathing engine combining the elements of a jet engine and rocket. Then the statement 2 says the engine has a low pressure compressor driven by a multi-stage turbine. And then the statement 3 has it is used in aircrafts where high speeds and low altitudes are required. Which of the following statements are correct? Okay, this is bit interesting question because we usually don't see a turbo rocket concepts in our propulsion classes, at least in engineering propulsion classes. First, before answering this question, let us see a schematic of how the turbo rocket engine would look like. So the turbo rocket engine as definition says that like it is a combination of turbojet and the rocket. So, and we know the turbojets are operating based on the air breathing concept, right? So they are the air breathing engines. So we have a turbojet that uses a set of fans or compressors that are run by a turbine. So where the air is being compressed. Okay. So this compressed air is then provided to rocket chamber where we will add an extra fuel to burn the high pressurized gas, and then we will raise the enthalpy of the system and we will allow it through the converging diverging nozzle to produce the thrust. So by schematic itself you can see that it is an air breathing engine. It is not non-air breathing engine. It's an air breathing engine because we are operating with compressors and other things where the air is being compressed. So the first statement now is not correct because they are saying it is a type of non-air breathing engine. So it is not true. It's a type of air breathing engine. And combining elements of jet engine and rocket, that is true, but non-air breathing engine is not true. So this statement is not true. And the engine has low pressure compressor driven by multi-stage turbine. Remember here the idea of using the turbine is to run the fan, not to produce anything else. So the multi-stage is not actually needed so to produce the required amount of work that is required to run the fans. So there will be a multi-stage compressor or fan, but not a multi-stage turbine in usual practice. So the statement true is also not correct here. Okay. And statement 3 is it is used in aircrafts where high speed and low altitudes are required. This is true because if I want to operate a rocket engine that uses the concept of air breathing, so that means it has to operate at an atmospheric conditions. So whenever we are operating a rocket engine in the low altitudes where the atmospheric air can be used to do the combustion, so that like it can avoid carrying any oxidizers along with that. So this is preferable in the low altitude and whenever we need a high speed because it is less weight in terms of engine, and we don't have to carry a fuel and oxidizer separately. So this is preferable over there. So from the options, the option C is correct. 3 only. Okay. So then we have a last question from a propulsion topic, that is consider the following statements regarding variation of thrust with the altitude. When the rocket propels, thrust increases with the increase in altitude because of decrease of atmospheric pressure. The statement 2 is thrust of a rocket engine is dependent on flight velocity unlike the gas turbine engine. And statement 3 is 40 to 60% of overall thrust changes may occur due to change in altitude. Okay, so in this question, if you simply see the idea of rocket, right, we use the staging concept. It's exactly because to compensate for a variation in altitude. So usually the thrust increases with increase in altitude for the rockets, because see, like if I have a rocket that is designed with certain nozzle geometry, so fixed geometry, and we are launching it from the sea level. So in the sea level we have say, like at sea level I have exit plane temperature and ambient temperatures are same, the perfectly expanded condition. So now as the rocket moves to higher altitudes, so what happens, since all other operation parameters are being constant, at least we can assume that to be constant, so the P exit plane pressure is not going to change. But what happens to ambient conditions? We know that from the standard atmospheric calculations, the ambient pressure decreases with altitude. So this nozzle is designed to produce a thrust, say m dot times VE plus PE minus PA times AE. So it will give you an optimum thrust when PE is equal to PA, and all other places we are going to expect a pressure thrust contribution. So since the altitude increases and this pressure decreases, so this part PE minus PA will increase. So that means it adds up the thrust as the rocket moves up in the altitude. So definitely as the altitude increases, we can see an increase in thrust in the rocket engines. So the statement 1 is true. Statement 2 says the thrust of a rocket engine is dependent on flight velocity. So this statement, you see, so in the thrust equation we never see a flight velocity coming into picture. So it depends on the exit plane velocity, not the flight velocity. So that statement is not true. It is not a dependent on flight velocity, whereas thrust power is dependent on the flight velocity but not the thrust. And the last one, 40 to 60% of overall thrust changes may occur. This is very hard to comment because no other information is given to calculate the thrust, and 40-60% is like really a huge number. So that's exactly why we use the concept of serial staging. So we don't want to have changes in that magnitude. So we will optimize the design according to the altitudes where it is operating. So we will optimize the nozzle. So like if I have a multi-stage, so I can use a different nozzle to operate at different altitudes. So the statement 3 is not true in that sense. So here the option 1 or the statement 1 is correct. Okay, so that concludes questions from this paper. If you have any doubt, you can actually raise here.